Welcome to The Explainer. Today we're diving into the wonderfully bizarre world of quantum mechanics. But forget the dense equations for a minute. We're going to make the impossible feel intuitive by following a young girl named Alice on a journey through a very, very strange land. So our story starts with Alice, and she is just completely bored with her very ordinary classical world. You know the one. It's a world governed by rules we all understand, where everything makes perfect sense and nothing is ever out of place. But the story immediately asks this really fascinating question. What if the rules that govern the very fabric of reality are far, far stranger than we can possibly imagine? And just like that, Alice's world is turned completely upside down. She trips, tumbles right through her TV screen, and lands in a place with a totally new set of rules: Quantumland. Her journey into the world of the very small has officially begun. Her first encounters? Well, they're with the fundamental residents of this world, the electrons, and they're about to introduce her to the first few bizarre rules of the game. So she meets this group of jittery electrons, right? But they're moving so fast she can't get a good look at them. And when she asks one to just stand still for a moment, well, something very strange happens. The electron explains this strange trade-off. To be a tiny, compact point, he has to move incredibly fast. To slow down, he has to spread out and become fuzzy. It's one or the other. And this right here is a brilliant illustration of one of the absolute cornerstones of quantum physics, the Heisenberg uncertainty principle. Think of it this way. You can know where a particle is, or you can know where it's going, but you can never, ever know both perfectly at the same time. There's always a fundamental trade-off. Alice then learns that not all particles play by the same rules. You've got electrons, they're what we call fermions, and they're pretty antisocial. They demand their own personal space. Then you have photons, which are bosons, and they're the total opposite. They're perfectly happy to bunch together in the exact same state. This strict rule for electrons is called the Pauli exclusion principle, and it's a big deal. The electron explains it to Alice with this great analogy of a train. No more than two electrons can sit in the same car, and even then they have to have opposite spins. This principle is literally what keeps atoms stable and prevents all matter from just collapsing in on itself. Okay, so how does all this activity get powered? To understand the local currency of Quantumland, Alice gets pointed toward this big, imposing building, the Heisenberg Bank. Here, the bank manager explains that in Quantumland, energy works a lot like money. The bank provides these short-term energy loans to so-called virtual particles, which lets them just pop into existence for a brief moment. And these loans, they aren't random. They're governed by another of Heisenberg's relations, and this one links energy and time. The bottom line is, the more energy you borrow, the less time you have with it. Now, this rule has some really profound consequences. If a virtual particle borrows a huge amount of energy to become really heavy, it has to pay it back almost instantly, so it can't travel far. But if it borrows just a tiny bit of energy, like a massless photon, it can exist for a much longer time. This simple analogy is actually how we explain why some fundamental forces have a very short range, while others, like electromagnetism, have an infinite one. So after leaving the bank, Alice starts to witness even stranger behaviors, things that seem to completely defy the logic of her classical world. She sees this character just repeatedly running at a solid locked door, and he's not trying to break it down. He explains he's trying to tunnel through, and after a few failed attempts, poof, he just vanishes from one side and appears on the other. Now, this sounds impossible, but it's a real quantum effect called tunneling. Classically, if you don't have enough energy to get over a wall, you just can't. But in the quantum world, there's a tiny but very real non-zero probability that a particle can just appear on the other side. And this effect is crucial for everything from nuclear fusion in the sun to the electronics in your pocket. Next, she stumbles upon a very strange construction site. The bricklayers are not carefully placing bricks one by one. Instead, they're just throwing them randomly in the general direction of a blueprint that's laid out on the ground. And here is the key takeaway. The foreman explains that they have no idea where any single brick will land. But here's the thing, they don't need to. That blueprint isn't a rigid plan, it's a probability map. Over thousands of throws, the bricks naturally build up according to that map, and a perfectly formed wall emerges right out of the chaos. Alice finally gets directions to the Institute of Mechanics, where she's hoping to get some real answers.
But the instructions she receives are by far the most baffling yet.
She's shown a wall with many, many doors. And to get to her destination, she's told she can't just pick one door to walk through. Nope, she has to go through all of them at the same time. This strange instruction is explained by the most fundamental and powerful rule in all of Quantumland. If an event can happen in multiple ways, a particle doesn't choose just one path. It takes them all. If it's not forbidden, it's compulsory. And this brilliantly illustrates the mind-bending concept of superposition. By taking all possible paths at once, the different possibilities actually interfere with each other. Some paths cancel each other out, while others reinforce one another, effectively guiding Alice to the most probable destination, the Institute. So Alice finally arrives at the Institute of Mechanics, and there she finds two figures playing a game of billiards that perfectly summarizes her entire crazy journey. On one hand, you have the classical mechanic. He lines up his shot with absolute precision, calculating every single angle. The result is perfectly predictable. But then you have the quantum mechanic. His shot is completely different. When he strikes the ball, it becomes a blurry wave of probabilities, spreading across the table. The ball's final position is a complete surprise, even to him, until the moment it drops into a pocket.
And this brings us to the final crucial question. If the fundamental building blocks of our universe behave with this much strangeness, obeying rules of probability, uncertainty, and superposition, why don't we see it? Why does our world seem so solid and predictable? It leaves us with a profound mystery. Where exactly does the bizarre quantum world end, and our familiar classical world begin?